Okay, so it's a pleasure to have Vincent Su from Berkeley here to tell us about wormhole-inspired teleportation on a quantum computer.
All right, yeah. Thanks so much to the organizers for giving me a chance to speak. I'm really excited to share this work with you all today. It's going to be a little bit different from the talks that you've heard before in that, this is not just like what you would do on a quantum computer in practice. Like I'm actually going to present some real results from an actual quantum device today. I have this caveat of wormhole inspired because as you'll see, the inspiration for this protocol definitely came from gravity, but I don't want to oversell the results and say that what I've probed really is quantum gravity in the lab. But as you'll see in a second, that's kind of where we're headed. So this is joint work we put out somewhat recently with collaborators at Lawrence Berkeley National Lab and Brian Swinkle, who's at Brandeis. Cool. So let me start with some motivation. And I also wanted to start with kind of some of the takeaways because the language of this talk is going to be probably somewhat different from the everyday language of most of the rest of the talks. I thought it might be a little bit too easy to get lost in the weeds, and I wanted to kind of get out up front, like what are the messages that I want to convey? So part of the power of ADS-CFT, right, is that the CFT doesn't involve gravitational degrees of freedom. And in that sense, like this duality is powerful. And the question I want to raise, I mean, it's been raised before, but I think it's an important question, which is what happens once we have universal quantum computers? This is obviously going to be quite some time from now, but nonetheless, the question is still interesting. The thing that I'll actually share the results for, right, is a demonstration of quantum teleportation, though there's some caveat here in that it's only a classical bit's worth, but it's on real quantum hardware without access to an experimentalist. Okay, so no graduate students were harmed during this project. And I want to claim that another reason why this work is interesting, right, is it's kind of one of the rare cases where quantum gravity tells us something about quantum information, right? Like we've seen tons of interesting results importing kind of the tools of quantum information. And so it's kind of nice to have some of that backflow and helping us learn something new, for example, this teleportation scheme. Yeah, and again, I want to say that, the experiment here definitely, by any stretch of the imagination, I think it's hard to say that it has a geometric dual, but right, the claim I want to make is that now is the time to start asking these types of questions on for kind of near-ish term devices. Okay. So to give you an overview of the talk, I'm going to talk about this wormhole-inspired teleportation. For those of you who are familiar, this is basically going to be teleportation by size. For this, when I was preparing this talk for this audience, I didn't really assume that this was something that is well known by this particular set of people. So I'm going to spend a little bit of time on that, but I'm also happy to go a little bit faster if this is something that has been seen before. And the theory behind this is really in all these papers. So the quantum gravity in the lab papers, and also this many body teleportation by scrambling paper that I think was out last year by now. The second half, I'm going to be talking about the experimental details, like what exactly, like at the end of the day, I claim that this is something I ran on a quantum computer, and I want to give you all the ingredients that actually went into that. And then at the end, I'll kind of have some discussion points on how this actually relates to gravity. This is more going to be a ask the audience type of thing, because I feel like people in this room have a lot more collective knowledge than I certainly have in this regard. So yeah, and by the way, I'm very happy to take questions at any point during the talk. Yeah, cool. Okay, so as a warm up, I just wanted to briefly review quantum teleportation like you would find in a textbook. So if you open up Nielsen and Chuang, this is what you'll find. The setup is that Alice has a qubit she wants to send to Bob. And unfortunately, she can't just like email it to Bob, but she does have his phone number. And at some point in the past, Alice and Bob arranged to have 2 halves of a bell pair. So that's what we have in our initial time slice here. And so Alice, with her half of the bell pair and her state, she performs a measurement in the bell basis on those 2 qubits. She calls Bob on the phone to tell him the results. And then Bob applies some poly operator that depends on the outcome of those bits. Okay, so hopefully this is nothing too crazy. I'm sure we've all seen this in some form or another. Just to briefly highlight some aspects of this, right? In order for this to work, in order for the classical bits to have been enough to send the information to the state, they needed this bell pair. You know, you can ask about causality, and it's not violated because Bob basically needs the classical bits in order to apply the right decoder. And this always succeeds with perfect fidelity. There's no question that Bob indeed has the state, assuming all the gates, all the operations are clean. Okay, so now let me introduce a second version of teleportation that's hopefully a little bit more unintuitive. So let's suppose we pick some Har-random unitary U that acts on n qubits. And now Alice and Bob share not just 1 bell pair, but n bell pairs. Okay, there's one other ingredient that I need to describe, which is a 2-sided coupling, which I'll call V, which takes the following form. It's a sum of correlated operators acting on the entangled pairs. Okay, so normally when you see like a ZZ term like this, it's like between nearest neighbors. But in this case, this is going to be coupling kind of left and right halves of these n bell pairs. Okay, so let me just describe in words what's going on in this picture. So now Alice has her qubit psi and her half of the bell pairs. She's going to apply U dagger. She's going to insert her state in. She's going to swap her qubit for one of the qubits that was initially part of this bell pair. Then she's going to apply U again. And then we're going to apply this coupling that acts kind of on entangled pairs as well. And Bob is told that he's supposed to apply U star at the end. Okay, so what do I want to say about this? Well, if quantum teleportation was unintuitive, then this thing, which is built out of Har-random unitaries, is should be even more surprising. Like, why is it that? Oh, sorry. Good. So the main claim about this circuit, okay, is that with high probability, psi is actually teleported with a fidelity that depends on the strength of this 2-sided coupling. Yes. That's right. So if you wanted to define teleportation that way, it's true, you can kind of make it more analogous by measuring the bits and then phoning them over and then doing the corresponding operation on the other side. I guess the point I'm trying to make is that kind of irrespective of that, the fact that you can think of the quantum channel going from this input leg to this output leg as being basically like a clean transmission, regardless of whether you chose to implement it via classical bits or not, or like this 2-sided operation as classical. Oh, sure. Yeah. Certainly. Yeah, good. So you're saying. Right, right. Yeah, I agree. Yeah, there's some unnaturalness in being able to kind of couple the two sides like this. So like, why would you do teleportation if you already had access in this way? But yeah, I guess the reason I'm introducing it like this is because in the actual experiment, we do use this kind of two-sided coupling as opposed to measuring and then doing a conditional operation.
Maybe I can ask the question in a different way.
Sure.
What were you not satisfied about with the previous algorithm such that you want to introduce this one? How is this one better?
Good. So let me say that there's not this type of in practice reason why I'm motivated to do this, other than I think it's cool that you can do it. And interesting to see it actually being done.
I mean, what I thought you were going to say is that you think this is more similar to the traversable wormhole. I mean, is that the motivation for this?
Yeah. So, I mean, yeah, that's basically what I was going to say in the next slide. Like, if somebody handed you the circuit, you'd be like, what's going on with this? But for this particular audience, as soon as I just like draw this picture, like it's suddenly not confusing in the slightest.
Yeah. But then you, maybe what you want to say is you're just trying to implement this, you're just trying to simulate the traversable wormhole.
Yeah.
You're going, it's not that there's some particular quantum task where, oh, Bob can send quantum bits to Alice,
No,
but Alice
that's right.
can only send classical bits to Bob, and then how does Alice send a quantum?
That's right.
That's the problem that the original algorithm solves. But
I see. Yeah,
you're trying to solve a different problem, which is how to simulate a traversable wormhole.
Right, but good. So like you want to say that the original teleportation is like a conversion between classical bits and entangled bits in order to send.
Yeah, that's how I think about it.
Yeah.
Say that the shared qubits come because maybe Bob sends half of an EPR pair to Alice, but say that Alice can't send qubits to Bob.
Yeah.
But Bob being able to send them to Alice and Alice being able to send classical bits to Bob is enough for Alice to also send quantum bits. That to me, that was the surprising feature of quantum teleportation.
Right. So good. So I'm not motivating it in the task operational sense.
I mean, you could probably phrase it in terms of some task where, so this e to the IGV is simple in some sense. Like you don't have to do a very complicated operation to get the information over. So in these systems, maybe it's some way of doing the task where you only had access to maybe a couple of qubits on each side.
Yeah, I mean, I guess the main point I'm trying to make is just like, if you didn't know about gravity, it would be very hard to find that this succeeds even in like the limited task of just like, I want to move this qubit from here to here. It's not the most efficient way, but it's a surprising way. Yes.
Maybe I'm sort of forgetting how this works, but I thought, can't you also do Gauss-Jeffreys wall more like actual teleportation? I mean,
that's the point I tried to make before, but maybe
Right, with the classical bit like use and
not couple these coherently, but just sort of transfer.
yes, yes.
A minor point is that you could invent a motivation by saying that imagine that an adversary can intercept the thing that's doing the coupling, each the IGV, right? And it would still be secure in this protocol, I believe. So there's some security motivation, like you use a quantum wire to send a message to do the coupling. The adversary, I think.
Is it because each individual coupling is like very weak?
Well, yeah, I mean, it's similar in that way. It's similar to sending classical information. So each of the IGV, if someone intercepts the classical information, unless they have access to the entangled bell pair, they can't get your qubit.
Gotcha. Thanks. Good. All right. So one other comment I want to make about this is this proof involves basically doing Haar integrals, but you can study, for example, instead of thinking of my time evolution as being this kind of Haar random unitary, if I instead studied evolution that was, say, governed by a Hamiltonian, then it turns out that you can study whether or not this succeeds without the machinery of Haar averaging by studying correlators that look like this. So just, roughly speaking, you insert your operator on the left at minus t and your operator on the right at time plus t. You study this correlators for all choices of O that act on the message you wanted to send. Okay, and at least for kind of concrete systems, this is a more amenable technique to study whether or not teleportation will succeed in your particular setup. Okay, so good. I think people already anticipated this slide as I expected, which was that the ingredients that I wrote down on the previous slide, while looking somewhat mysterious, are basically what would happen if you took Gauss-Jaffer-Swall and you literally tried to transcribe it and put it on a quantum circuit. So in that sense, it's maybe less confusing. Okay, so I mean, one question you can ask about this that's kind of surprising is, given this inspiration from from traversal wormholes, like, why does this work in theories without a gravitational dual? And this question obviously was answered, but I want to emphasize it's kind of surprising. And so it has to do with this quantum mechanical notion of operator size, very basic in quantum mechanics. So any qubit operator, you can just expand in a basis of polystrings. And then if you take the coefficients and you rearrange them and you ask about the support on polystrings of different lengths, that gives you this size distribution. And, I guess I want to signpost that this is something that I still just find fascinating, which is that, quantum gravity gave us a hint about something we thought we already figured out. Like, obviously people had studied operator size before, but this additional structure of so-called size winding that exists, I don't really know of any other way that people thought to think about this object. Even though it's purely quantum mechanical. So my goal for the next couple slides is to slightly demystify this for people who aren't experts on this. And I want to talk about this two-sided interaction that we've spent some time talking about. And the most basic calculation you need to understand what goes on here is to consider states, which are basically, starting from a Bell pair and then acting by some poly on the right side, say. Okay, and the claim is that this state is actually an eigenstate of the type of term that shows up in the two-sided coupling. The calculation is obviously very straightforward. When you act with these correlated z's, the only thing you have to worry about is whether or not it has to commute past this. It either anti-commutes or commutes because it's a poly operator. And so you get that this state is a plus or minus eigenstate. Okay, so if you measure the effect of this kind of total coupling, essentially what it's asking is the way I like to think about it is you take a Z operator and you slide it past your polystring, and it basically counts the number of terms that don't commute. At least in this basis. Okay, so then the effect of this coupling is basically to apply some size dependent phase. So in general, your operator is going to be a sum of polyterms. On each individual polyterm, it's going to look like this. And so you get some, so this is what it looks like in the eigenbasis. Okay, so kind of to bring it back together, the very rough picture, and here I'm going to talk about just the infinite temperature case without the connection to gravity, but the rough picture that, say, I like to have is you consider some local excitation on the left under, say, generic scrambling dynamics. As you time evolve it, the kind of spatial extent of that operator grows. And if you wait long enough, right, then the support in the size of the size distribution basically gets peaked at the system size. And then if the support of this is of this operator O of L is peaked at the system size, then this coupling will basically act like an overall phase. Okay, and so that's what allows you to see that then this correlator, which I introduced on the last slide, but kind of drew diagrammatically here, that this correlator will have maximal overlap because you essentially get something that looks like two operators, like two correlated operators acting in the Bell state. Okay. Good. So this is just for a single operator. Again, if you want to study whether or not this general circuit like this will teleport a full qubit, you need to consider all the operators that could act on that qubit. And they have to be kind of correlated in a specific way for it to teleport the message. Yeah.
Here you're a certain structure, certain operator, so the type operator, the time solution operator.
Yeah.
In the Bell theory, there are some symmetries.
Yeah. Oh. Yeah. I see what you're saying, but I think this is one of those things that, like, at least at the level of this setup, you would like to give it some geometric meaning, but like, you know, everything I've defined here is just in terms of poly operators, which, like, because we're talking about the boundary theory, presumably it's just always there. And, you know, whether or not it actually corresponds to some sort of bulk symmetry like that is, like, I guess what I would say is that this alone is definitely not enough. Yes, that's correct. Yeah. That's right. Yeah. Yeah, good. This will also kind of come up when I talk about the actual system that I'm using for time evolution in a bit. But I mean, it'll be kind of clear there that on the last slide, yes, but the thing I'll tell you about is not a Har random U. Yeah. Exactly.
I'm sorry, I got a little lost there. When you say OL acting on phi as an eigenstate, you mean eigenstate of V or of,
yes, and then as a result,
so then either the IGV
it's just an overall
produces a
phase.
phase.
Yes.
So is it still coupling?
Well, it is because it's like a result. It's out of a direct interaction between them, but the interaction doesn't change, like leaves you in the state alone, and so you can almost pull it out. Okay. Cool. So, right, with this in mind, the goal of this project is then to observe some sort of teleportation signal as a function of this two-sided coupling G. I mentioned this very briefly, but in the Har random case, you can actually characterize the channel that describes evolution from, oops, sorry, from this qubit to this register out here. Okay, and let me just break this down. This is a little bit cryptic, perhaps, for this audience. So what happens here is that given some density matrix, it takes an input state here, and what it first does is it what we call degrades this state. So by degradation, okay, if you want the math definition, it's this guy. It's a linear combination of the original state and the maximally mixed state. So it's kind of basically like pulling you closer to maximally mixed, if you think about it on the block sphere. By an amount lambda. And then the y's on the outside basically say it's like a bit flip if you're in the z basis or the x basis. Okay, so the kind of key signature that we're looking for is that the amount of degradation in the Haar random case is a function of g actually, and it depends like 1 minus cosine g over 2. Good. So the claim is to like we want to look for something like this on a quantum device. Good. Yeah. Yes. Yes. Yeah. Mm-hmm. No, it has to do with the fact that the coupling is normalized. The two-sided coupling is normalized, like per qubit, but sorry, maybe I missed the end of that. I missed the possible resolution to your question, or?
Well, the period, this has that periodicity, you know, the eigenvalues of D all have to be integers.
Right.
So, well, yeah, it was this, so the spin thing is just I forget what it is, but it's under
right. So good. So yeah. So good. So the technical full size operator is like, well, actually, sorry. Let me go to this. Well, they are for because you have two of them on the left and the right. They always come in pairs. No, they do commute with each other because you have two of them. Yeah. 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 So the exercise of this slide was basically to say, like, just take one term in that, and then say one term in your polystring. Then the effect of this coupling is basically to test whether or not it commutes with Z. And so it's kind of like measuring the poly weight if you only cared about X and Y. And then you take a sum of like ZZ, XX, and YY. Yeah. Uh-huh.
What else do you do? You know, if it starts out as your own periodic, then I'm probably going to draw that. What specialty are you looking for?
Right. Yeah. Yeah. Oh yeah. So well, the original question was, you know, what's the actual signal you're looking for if it's just like starts at 0 and it's some periodic function, and then Juan was just pointing out that, you know, it's pretty non-trivial that you can get a fidelity 1 by such an operation. So that's what we're going to be after indeed. Okay, so just to give you, so now we're kind of in the second part of the talk where I'll explain all the building blocks. So again, I'm not really assuming a ton of familiarity with quantum circuits in this audience, so definitely let me know if there's anything I can clarify. So I'm going to introduce the model, this chaotic spin chain. That's going to generate the time evolution in place of the hard random unitary. I'll say a little bit about kind of what goes into thinking about these hardware considerations, right? It's not quite as easy as saying, here's my circuit, go run it, but so I just want to give a flavor of some of those considerations. And then I'll share kind of explicitly. So I kind of characterize this hard random case as degradation followed by a bit flip. I'll be able to tell you the channel we get as a result of running this as our time evolution, and then I'll share the kind of actual hardware results. Okay, so the model we're using is actually pretty simple. It's called, depending on who you ask, some people like to refer to it as the kicked quantum Ising model. And you can roughly think about it as an Ising model that's split up into two parts. Okay, so we kind of artificially separate the z terms and the x terms. So every time step involves, you can kind of think about it as like alternating layers. The first layer is the interacting layer that does the nearest neighbor interactions and has an on-site magnetic field with varying strengths. So this is kind of where randomness comes in. And then after you finish that, the second layer involves these transverse fields with uniform strength. Okay. Now you might ask, why this model? Why not just like the Ising model or something? And the reason is because this model has been well studied as a really toy model of quantum chaos. The previous paper showed that basically you asked about the entanglement growth. It spreads as fast as possible at this critical point in parameter space. And that actually, if you compute the spectral form factor for this thing at large system sizes, it looks random matrix-like. And there's one more thing I should say about this, which is that the fact that these layers of time evolution are alternating is actually pretty nice, because if you look at everything that makes this part up, it actually, like all of the terms commute, and likewise over here, so you don't have to worry about trotterization errors. Yeah, good. Okay. Let me see. Okay, I'm doing okay on time. Good. So this is the part I alluded to about just wanting to give a slight flavor about the state of quantum circuits. And people often like to say we're in the noisy intermediate scale quantum regime, a coin termed by Preskill a few years back. And I guess I really want to emphasize this noisy part. And in particular, 2 qubit gates are really expensive because they're a lot less precise than single qubit gates. And this term precise is, well, an industry of its own in characterizing noise. But usually when you hand like an experimentalist a circuit, the first thing they'll look at is like the 2 qubit gate count. Because suppose that every 2 qubit gate works with 98% fidelity, right? As soon as you have like 20 gates, almost like a lower bound on how bad it could be is like is that 60%. And so, a fun game you can play is to say, let's suppose I was debating between 2 types of quantum computing layouts. Okay, one is kind of like these back-to-back chains, and the other one is this kind of spread out board game looking layout. And you might think that given the model is bell pairs between 2 1D chains, that this would very easily reduce like the gate count of our problem, right? Here you could probably fit 2 1D chains, but initializing those in a bell pair in a entangled state beforehand would then be more expensive. But it turns out that the way that current devices are now, like actually this is what we ended up getting better results from. So I guess maybe going back to the question of like, what would you hope to see? Well, I'm just setting it up that there's a lot of ingredients that need to go right in order for you to be able to see this order 1 fidelity.
Are these specific layouts of actually existing?
Yes, yes.
What are they?
So they're from, oh, I should have put this, but they're from IBM's available quantum devices. I forget the names, but
They're both IBM.
they're both IBM. Yeah.
And in both cases, each dot is a qubit.
Yes, yes, yes. Yes, thank you for asking these.
And the lines mean that any operation is allowed, or what kind of operators can you do on 2 qubits?
Good. So I believe that their native 2 qubit gate is just like C naughts. So if you wanted to do like a ZZ, you would have to do some extra overhead. Yeah.
Two questions actually. Number one is this a universal statement that like more qubit gates are like worse than lesser? 2 qubit gates.
It's not a universal truth, but it's
like as in if I use a different quantum technology, like.
Yeah, I would say it's universally acknowledged.
That is to say like different quantum technologies will like I say.
Oh yes, certainly, and people are people are certainly trying to get these error rates down. The other part is just like it's very hard to characterize. Like, what does it mean for a 2 qubit gate to have gone wrong? Like, did you like slightly over or under rotate? Like, did you just like miss completely? Is it like decoherent noise? And so that's why like coming up with a single number is just a hard business.
And just to be entirely sure, like that there is some circuit that you have for this wormhole teleportation, right?
Yeah, I'm going to show that in a
Oh.
second. Yeah, good. Yeah, other questions? Why not? Oh, I see. Like if, okay. Right, so yeah, good. So from a kind of greedy, I want my circuit to run perspective, I think I do want them to be local, but I think if I'm understanding you correctly, like you kind of want to say, you know, really these are like 2 separate systems and we like only interact with them via this coupling. And so we don't want accidental, say, crosstalk to have. Oh, I see. Wait, really? I mean, it's still only coupled to like nearest neighbors though. Like, I mean, I guess you have some, yeah. Like it's not like because of this layout, they have higher order gates. Like it's still 2-body terms, I guess. But yeah, I see. That makes sense. Okay, good. So then there's this whole other business of estimating the effective error and like, you know, giving reasonable estimates to have confidence on saying like, you know, how can I extract the signal from the data? And I guess I'll just highlight here that if you want to learn more about these, they're described in the paper. And also we've put out like an open source package that you can just go look at and play around with if you want. Okay, so good. Back to the question of, okay, what's the circuit we're actually running? So given these realistic error rates and this kicked quantumizing model, the experiment that we ended up running at the end of the day consists of 7 qubits, 3 on the left, 3 on the right, 1 for the message qubit. Just for the sake of ease, we're going to initialize our qubit to be the plus eigenstate of Z and then just measure the expectation value in the output qubit. Okay, so it turns out that under that set of constraints, there's a lot of parameters floating around. And so what what we ended up actually implementing was basically 3 time steps of this kicked quantumizing model with 0 on-site field, and that was kind of expressly for the purpose of this. So you lose some of the randomness properties, but we really wanted to see teleportation, so that's what we are maximizing. And then if you ask, what does this circuit do? I'll show a picture in the next slide. Well, maybe I'll just show it now. So here's, yeah, good. So here's a diagram. It didn't like to spit out very long, so really the ends of this are connected like this. Good. So there's 7 qubits here with a classical bit for the measurement outcome. This part here is making the bell pairs. The rest of this top half is 3 steps of negative time evolution. Here we're inserting our message into the circuit and then running time evolution back forward. Okay, and then let's see. Oh wait, where's the coupling? Okay, I think there must have been some, let me see here, where's the coupling? This can't be it. Oh, okay, it's these 2, sorry. These 2 are the coupling. There's only 2 qubits that needed to be coupled this way. And then we have time evolution on the right. Okay, so pretty simple, pretty neat. You could draw some squares. Does some teleportation for you. So the effect of this, yes. Yeah, sorry. It's this was just a function of the printing mechanism. It didn't want to print wide, so it printed tall. And so it's like a music stand. Yeah. Yes. Yeah. Sorry. Okay, so this is like everything I've described in words, now in a picture. And you can ask what this thing does. And it turns out that it is pretty close to what the Haar random channel does. So you have your final bit flips. You have your degrading, depolarizing channel. But there's one more thing on the inside, which is a dephasing channel. I've written the explicit action here, but let me just draw a picture because I think it demonstrates this better. So suppose you had your qubit that was initialized here on the block sphere. Okay, the effect of this dephasing channel is to basically project it onto the z-axis. Okay, so good. So what it means basically is if you were to send in a plus or a minus state, you would effectively get maximally mixed out. And if you were to send in a plus or minus a 0 or 1 state, then you should get out, actually bit flipped because of these y's hanging around on the outside. Okay, but there's still this characteristic magnitude that's set by the two-sided coupling. Okay. So here's the circuit again. Okay, and now here's the actual circuit that has been compiled down to the native gate set. So, as theorists, we like to work with just like 4 gates. Okay, but that's not what experimentalists actually have. I don't really expect you to get much out of this other than that here there are a lot more gates to actually be done. And so, yeah, this was roughly, we wanted to do this for larger system sizes, but already for 3 qubits per side, like this is the type of circuit that we had to deal with. Good. So the question is, why am I running this and not this? And they're logically the same. This is what I would, this is the language I would speak. And then this is the language that their computer would speak. Yeah, exactly. Right. Okay, so then I gave this spiel about 2 cubic gates. Here, this is like already the work of optimizing and optimizing to make this number of 2 cubic gates the smallest it could be. And even then, it was like about 40. Good. Okay, so finally here are the results. So the dashed purple line here is kind of what you would expect based on numerics. This yes, sorry, yeah, I forgot to mention this. Basically, this Y bit flip on the channel means that if you sent in a +1 state, you would get a minus. You get the 1 state instead of the 0. Yeah, so just I should put a minus sign on this whole plot. Yeah. Yeah, well, and then you'd be like, well, you manipulated the data to look good. So yeah, good. So, raw out of IBM, we see maybe like 20% of the signal using some of the techniques that I alluded to in the paper. We can reasonably estimate that the true signal is something like 35% of the fidelity. Okay, so this was on IBM's computer. At some point, we got very limited runtime on a different machine, which was Honeywell's computer. And here I'm plotting the same experiment. I mean, obviously compiled slightly differently, but notice that these are basically raw output measurements as opposed to, this is without error mitigation yet. And we start to see signals of like order 80% of the fidelity. Yeah, I guess it's suitable for this problem. Yeah. Oh. Yeah, sorry. It's yeah. I believe the trapped ion machines have better connectivity and better 2 qubit fidelity. Yeah. Oh yeah. No, that's right. So like I was saying before, there are a variety of things that can go wrong when you try to implement some quantum gate. So there's broadly separated into 2 types. One is coherent error and one is decoherent error. The coherent error is like you over-rotate or under-rotate slightly. And so the thing that you do to combat that is you basically insert factors of the identity and then average over them. So what I mean by that is like, let's say you take a C0 gate and then you like apply X right before and X right after. Well, I'm not sure if that specific combination works, but it should be such that you can basically push them past. And then you would get a different measurement that gives you, and then you average over different choices of identity, logical identities. And then you can estimate kind of how much your signal is well, I guess that is more for accuracy rather than degradation. Exactly. And then you can say, well, if I numerically do this, how much does this, then I can estimate the magnitude of that and then just multiply back, but I have a more accurate answer. Yeah, so some mix of both. I mean, yeah, on the left we were really like, okay, is this convincing? Like, if I showed this to somebody, would they believe it? And then it's like, okay, well, what can we do to make it look better? Yeah. Okay, good. Logically, yes, but I mean, when you compile it, no. I don't have the, yeah, I don't have like the kind of, Yeah. Yeah, no, I don't have that figure.
By the Honeywell. All right,
Yeah.
The analytical is for large N?
No, for,
For any-
yeah, exactly. Like specific to the, basically, yeah, this thing. Okay. Cool. All right, so cool. We're able to transmit a classical bit's worth of info. I say it's a classical bit because of this dephasing noise, but really, it's still like the quantum state. There's no, like, if Bob were on the other side, he would genuinely have this the spin as a quantum state. And it's kind of cool that you can work out precisely like why you get this channel based on how sizes work under this model. And the point again I want to reemphasize is like hardware is advancing to the point where, even though it's kind of tough to get things out, non-experimentalists can do cool things too. And I think that is a sign that things are getting interesting. Okay, so.
Sorry, can I just ask
Yeah.
another terminology? When you say you transmitted a classical bits worth of info, do you mean a half a qubit, or what do you mean by that?
Yeah, so this is, I agree. I was having a little bit of trouble of figuring the best terminology for this, but what I mean by that is about this dephasing aspect, where it's not true that you can send in any state on the Block sphere and get it out. It's only when it because of this projection onto the z-axis, you can only successfully teleport like the states along the z-axis in the Block sphere.
So, because that's for the the wormhole, that's not true, right? So the wormhole
That's right.
Information goes through. So
That's right.
Maybe I'm sure you explained this. I just didn't understand. So why is there this? Why do you lose this phase information?
Yeah, it's because we're doing a very toy spin chain model that is not, not really effective gravitational description. But like, I don't think it has a
I
dual.
understand that, but you just wrote down. In the beginning, you just wrote down some quantum algorithm, right? It didn't look
Right. So that was with hard random as well.
Oh, so you say the problem is because your U's are not random enough somehow?
Yeah.
If you could perfectly implement the circuit, would you be able to send the qubit, or would you be able to only send the classical qubit?
This circuit,
Yeah, this circuit, this particular circuit. Like, is it because of the
not an arbitrary qubit, but a qubit that is Z aligned. Yes. Or if you want a pure state out, you have to start with either plus or minus. 0 or 1.
It's not related to the noise of the actual experiment, even if you had no noise.
That's correct. So this expression is a function of this like finite n spin chain model. Yeah, at this set of parameters. There could be, if maybe if you make the system size larger, you play around with some of the weights, you can get something different. But
if the only problem is that you can't make a random unitary, then shouldn't like 2 designs or whatever be good enough, and those don't sound that big?
Sorry, I'm not sure I understand the question, but like, do you want to say like, is your question whether or not we can do something similar on a quantum device that does the full state teleportation?
Yeah. I just want to do, I forget what you called it, but your second algorithm in the beginning of the talk.
Yeah. Good. So in principle, yes, but as a function of like system size and what's achievable, we didn't find that. So I think you could, if in like say the next year's quantum computer comes out or something. But for this, under this kind of set of constraints, this is the channel we get.
A little bit, I feel like you should be able to, sorry, the issue that the unitary is not, okay,
Yeah, yeah, right. Yeah. And I mean, again, this Honeywell thing was like a last minute addition. So
Yeah.
when we were getting like 20% fidelity out of already like these very small system sizes, we were like, okay, well, anymore, and it's like you're really pushing it there.
Yeah.
I would have thought that the early time versus the wormhole tech would be
Easier to see.
Hard right, but the very late time.
Yeah. That's right. So let me see. It turns out that to see that you need slightly bigger system sizes. So that was kind of the main bottleneck for that. But I agree. Yeah. Yes.
Can you characterize, so you were saying you were struggling a bit with characterizing this as a classical bit, and I understand the choice, but is there a way to make this more precise? You know that asymptotically, like people like Hayden and Pennington have written down these formulas where one alpha bit is one alpha qubits or whatever, one bit is one e bit and 2 0 bits. Is there some way that you can say asymptotically, this is really just going to be n classical bits, or is it going to be n classical bits plus some other stuff?
Yeah, that's a very interesting question. That I don't know the answer to, but yeah, I'll think about it. Yeah. So this was kind of the most precise way that I could think of writing down the effect. Okay. Good. Cool. So yeah, like people have kind of already started to point out, right? Like the thing that I said actually had very little to do with black holes. You take any quantum chaotic system and this should in principle work. I didn't really have time to tell you about this more specific form of size-based teleportation that is relevant for gravitational systems. If you want, should read the paper by Henry and friends. But just at a high level, I guess I'll share that the effect of this teleportation, at least in our case, really worked because, you know, bell pairs, you can just push things around and things are very well correlated. It's more surprising that you can do this when you have finite temperature TFD states. And so in systems with a gravitational dual, you would expect that this teleportation signature to look drastically different. Kind of start to wrap up, you know, I know this talk has been probably in a slightly different language, but even though this experiment doesn't probe quantum gravity in the lab, I think that the results are encouraging enough to really start thinking about like what questions we would want to ask given upcoming available hardware. I think it's interesting that non-experimentalists can run meaningful calculations. And if you talk with people who build quantum systems, they're very open to design influence. They like love to find problems that people are interested in and care about. And they ask like, what do you need? And so I think as a field right now, we don't really have good answers for like what we want. And if we care about getting to this goal faster, it's important to have that vision so that it can kind of influence the way that these systems are built. And again, this is a very like toy model, not very gravitational in any sense, but you know, I'm optimistic that we'll start to see experiments soon that are maybe more interesting from a gravitational perspective. As one kind of cool application of this, you might use it as a holography finder. So, you know, right now we only have SYK as kind of our playground for a quantum mechanical system that has a gravity dual. But in principle, if somebody were to come up with a new one day and say, oh, I think this has gravitational dual, you know, this would be a one-way check, like a diagnostic to see, does it at least pass this traversable wormhole test? Okay, and I'll just end with some final speculative thoughts. Now, I think this is the right audience to ask these questions, right? But like, when can we really say that this protocol has probed the bulk? Yeah, it's really not. It's not clear to me like what would be a convincing measurement in the boundary that says you learned something about the bulk. Some other things you might play around with in this regime, or maybe if you hide something behind the horizon, could you design an experiment that tells you that you scattered off something in there? And another kind of related question to a theme that came up this week, does this work for non TFD initial states, right? Like how special is the TFD for having these connected geometries? And you know, a little further down the line, like, do quantum computers being finite n really ruin our chances of quantum gravity in the lab? It's, yeah, I don't know. It's, I don't know the answer, but I'm curious to hear people's thoughts. And of course, you know, bulk reconstruction of is a very important question that would be good to investigate in like concrete quantum mechanical models. With that, that's all I have. Thanks for your attention.
All right, thanks, Vincent. So any more questions from the audience over there?
So a small remark to be made about the non-TFD initial states is that in this Frey-Vogel paper where they have these fidelity, like the overlap between TFD states and the ground states of these approximate Hamiltonians that you can build out of them. They may not be due to like some geometric state in the bulk, but like it is, yeah, you can still see correlation, like causal correlations.
Right.
Between the two
Right.
sides. Yeah. Even in say SYK.
Even what?
Even in SYK had some like weird coupling or some other spin shift.
Right.
Yeah. Also, a quick question. What do you mean by wormhole tomography? Like,
Oh yeah. So for example, we expect that behind the horizon, there's like nothing waiting for you there. And so in principle, if you were to fall in, like that, like the reason you come out so cleanly is because there's nothing behind the horizon. And so it'd be interesting to ask whether you could kind of engineer things to be behind the horizon that you can then ask the person who presumably went through.
but from the boundary side, like from.
Oh yeah, sorry. I don't mean good. So I don't mean tomography in the quantum state tomography sense on the boundary. Yeah. Yeah.
I have a comment regarding the discussion we had at the very beginning.
Yes.
And maybe it's just terminology. Actually, it is only terminology, but I would say from a quantum information perspective, what you're actually doing is something called quantum one-time pad encryption. And actually a coherent version of that. And as I think Henry pointed out, the task that you're carrying out is, of course, not sending a quantum state using classical bits, but you are basically using entanglement to send a quantum system in such a way that someone who didn't have a chance to get hold of the entanglement couldn't intercept it. And I think if you look at the protocol for what is known in our community as quantum one-time pad encryption, it's basically what you're doing, but it's usually, let's say, you can do it even classically. So instead of sharing entanglement, it would be sufficient to have classical correlation. So yours is basically a coherent version of that.
I see.
So
okay.
I would say you should probably rename it, and then it's more accurate for the
Sure. Yeah.
quantum information community.
Thanks for that point. Yeah, that's very helpful.
Would you do the other version of teleportation, measure it, and then do the operation on the other side? I mean, have you tried to do that, or it doesn't work, or maybe you know theoretically that this model doesn't work?
I don't see any reason why it wouldn't work. There's yeah, good. So in principle, I don't see any reason why this wouldn't work. I would say that there are some just like kind of weird lost in translation effects, depending on whose hardware you're trying to use. Like some people don't let you do this conditional measurement based on the outcome in the, like when you go to like write up the program.
But you can just do it in that you can do it in a unitary way, right? You just you delay the measurement. You just sort of use a unitary.
Yeah, there's nothing wrong with the unitarity of it. They just like literally don't have that functionality built in sometimes. I know it's petty, but I mean, I guess that could also just be done numerically. So I mean, what would you want to see differently? Okay, yeah.
People have certainly done quantum teleportation, haven't they? Experimentally.
No, but
Yeah, I thought this is. What do you mean in this setup though? Because I thought people have experimentally implemented the original quantum teleportation protocol.
He wants to do the classical transmission of the two-sided coupling.
Uh-huh. Uh-huh. But I
Right.
thought you don't need the V then, right? If you're going to do quantum teleportation, then that replaces the thing with the V.
Yeah, that's so you replace it, you use the same element, like you measure the same.
Oh, I see.
On the left, and then you send information to the right, and then you do something.
Yeah, I agree.
The theoretical question is that like gives the same answer. No. I mean, in the case of the wormhole, it does give the same answer.
Right. I suspect actually what would happen is you probably need to have larger system sizes, right? Because the measurement is going to be okay. Yeah, I don't know. This is an interesting. I mean, yeah, it seems like an answerable question.
Anyone else? Maybe I'll just comment. I agree with the last thing you said. It's kind of embarrassing. You know, I also, these experimental analysts always are coming to me and saying, oh, you know, I have 100 qubits. Please tell me something to do with them that you care about. And I never can, you know, I don't know. I mean, I didn't think about it that much. I thought about it a little bit.
They're absolutely desperate.
Yeah. And I don't know if it says what it says about us as a field that we can't give them a good answer to this question, or we haven't yet. I mean, maybe that's okay. We're just talking past each other, but it would be nice if there was something we could tell them.
I think they like us because we give them stuff to do.
Yeah. But I mean, so far we give them stuff to do where we already think we know what happens, right? What would be great is if we could give them something where we don't already know what happens. That's what they really want, right? And that would also be better for us, right? I mean, checking Juan's algebra that ADS equals 15 is great, right? But, yeah. Can we do better than that? All right, let's thank Vincent.